Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture, if you recall, we just talked about the potential energy, complementary energy, and then the conservative system, and then based on that we derived one relation, that is del u star del pi is equal to delta I, right. That means, if you take the partial derivative with respect to a particular force pi, okay, of the complementary energy, then that will give you the deformation or the deflection, okay, along the line of action of pi, that load pi. Okay. So, based on that, actually Castigliano's theorem has been developed, and that theorem says that in case of external forces, in case of external forces acting on a system subjected to deflections which are small, if the total complementary energy u star, okay, of the elastic system is expressed in terms of the loads, then the inline deflection at any particular loading point is obtained by differentiating u star, that is a complementary energy, with respect to the load acting at that point. So, this is the theorem. Okay. So, that means the theorem says del u star by del p I is equal to delta I. Already we have derived this thing in the last lecture. Now, Castigliano's theorem says that in case of external forces acting on a system subjected to deflections which are small, of course, we are talking about the small deflection problem or small deformation problem. So, if the total complementary energy of the elastic system is expressed in terms of the loads, so different loads, okay, which are applied on the body, on the system, conservative system, the inline deflection at any particular loading point, okay, is obtained by differentiating the complementary energy u star with respect to the load acting at that point. So, this is the total complementary energy of that particular elastic system, and we are differentiating that with respect to a particular load, say Pi, and that will give me the deflection okay, deflection at the point where pi is applied. So, this is delta I. Okay. So, by using this theorem we can find out the deflection as well as deformation under different elastic system under different kind of loading system. Okay. So, let us see before going to or before jumping to that particular or different cases or situations. Okay. Now, we will be talking about only, so far we were talking about the nonlinear system. Now, so far in this particular course we are dealing with the linear system. Okay. So, if you consider the linear system, then basically if you consider the linear system, okay, linear elastic system if you consider, and then if you try to plot f versus delta curve. So, as you know that will be linear. Okay. So, therefore, this is say O, say E, this point say E1 and this point say E2. So, okay. So, if you consider linear system, so OE will be the plot, will be the relation between f versus delta for linear system, as you have already seen in earlier discussion. So, your potential energy is nothing but the area of, as per our definition, O E E1, okay, area of O E E1, that is the area under the curve OE. Okay. Similarly, your complementary energy is nothing but area of O E E2. Okay. So, for your linear system, as you know, this line of course will be the 45 degree. So, if for a linear system your potential energy must be equal to the complementary energy. So, that means your U is equal to U star, which was not the case in case of nonlinear system, right, because at that time this OE line was not straight line, that was a nonlinear line. Okay. But if you deal with the linear system, then we can very much write that U is equal to U star. Okay. So, now if you write E is equal to U star, so therefore, from this figure actually we can write U, that is nothing but the potential energy, which is nothing but half into delta into F. Can I write that? So, that is the area of the triangle OE E1. Similarly, U star can be written as half into F delta. They are same for a linear system. Okay. So, that is the area of triangle OE E2. Okay. So, this now onward actually, because we are dealing with the linear system in this particular course. So, now onward this we will be using one common term for potential energy or complementary energy whatever, and which is known as elastic energy or the strain energy. Okay. So, that is the common term which will be used as instead of potential energy or the complementary energy, because both are saying we are going to use one common term, that is elastic energy or strain energy. Okay. So, energy stored due to deformation, okay, or the elastic, I mean energy which is stored in the elastic system. Okay. So, this will be your common term. Now, already you have seen that you have written, say, I mean in earlier case del u star del p I is equal to delta I. Now, what was that? That means, if you take the partial derivative of the total complementary energy, okay, of the system with respect to P I, load P I, then you will be getting the deflection at that particular point I. Okay. Similarly, if you try to take the partial derivative with respect to partial derivative of the complementary energy with respect to say moment m I, okay, some moment, because there are say consider the elastic conservative system is experiencing several moments, okay, say m1 to mi, mn. Okay. So, now if you consider or if you take the partial derivative of the total say complementary energy with respect to mi, so that will give you the rotation at that particular point with respect to the same axis, okay, of the moment. Okay. So, that is your phi I. So, that relation is also applicable, because moment only creates rotation and the force, that is linear, I mean axial force, okay, will cause the deflection, right, and the deformation, that already we have seen. So, this is, as this one is valid, this is also valid, and we will be using these things frequently. Okay. So, now if you want to find out a rotation at a particular point, so you find out the moment which is causing the rotation at that particular point, and then you take the partial derivative with respect to that particular moment, you will get the rotation. Well, so now onward we will be calling for a linear system. Okay, we will be calling the complementary energy or the potential energy by a common term as defined. So, that is your strain energy or the elastic energy. Now, if you consider the basic systems, say one spring, and you are applying a force F, and for that you are observing deflection delta, and the length of the spring say L. Okay. So, as you know, your F is nothing but K delta, where K is nothing but the spring constant or the stiffness of the spring. So, your U now onward we will be using only U, which is nothing but your strain energy or the elastic energy, okay, and it will take care of both complementary energy or the potential energy, because we are using the common term. So, U is equal to half F delta, just now we have seen. Now, in place of F, if we put K delta, so I can write this thing half K delta square, that means the strain energy is expressed in terms of only delta, or it can be rather expressed as half F square by 2K. That means, the strain energy can be expressed in terms of only force. Okay. Agreed? Fine. So, now if I consider a linear system, so for this is the strain energy. What is this? This is the strain energy, okay, stored in the spring due to the application of this force F. Okay. Now, if I consider a uniaxial say member, we have seen that thing earlier also. The original length of the member is say L, and we are applying an axial force say F, and due to that axial force you are getting some elongation in the member, okay, and now the length is say L plus delta, okay, and the cross sectional area of the member is say A. So, by our previous discussion we can say that delta is equal to FL by A. Already we have derived that, already we have seen that, nothing new actually. Okay. So, now or from this I can write F equal to A delta by L, okay, A delta by L. So, now if I want to find out the strain energy for this system which is under the load F, then we can write down half F delta, that is the area under the curve, okay. So, in place of F I can write this A delta by L into delta, which can be written as A by 2L delta square, or it can be further written as, so this is in terms of deflection, I mean deformation delta, okay. So, or it can be written as F square L by twice A. So, if you want to express in terms of force, that is here, if you want to express in terms of deformation, that is here. So, this is the strain energy of the system under this kind of axial force. Okay. So, now what basically you are getting, I mean from the Castigliano's theorem. So, suppose this is the strain energy, right. So, this one is your strain energy. So, for this kind of system your strain energy has been calculated like that. So, this is my strain energy, say F square L by twice A, this is your strain energy. Okay. Now, you want to find out delta, and if I want to find out delta, delta means that is the deformation which is along the line of action of force F, applied force F, right, tension. Okay. So, now if I do this operation del u del f, I should get delta as per our Castigliano's theorem. So, del u del f is nothing but, if you see from here, and this is nothing but so that already we know, I mean basically why I am showing this problem, because we know the solution, the delta is equal to FL by AE. So, from the Castigliano's theorem we have got it, right. So, if we manage to get or manage to find out the strain energy of a particular system, then if we take the partial derivative with respect to that force, okay, along which we are concerned to find out the deflection or the deformation, then we can find out. Okay. So, this one is your, this is coming from your Castigliano's theorem. So, now what we will do, one thing is very clear, that if we manage to get the strain energy for an elastic system under different types of loading, okay, different types of loading means, as you know from the previous discussion, that you may have the member under torsion, you may have the member under bending. So, there are several kinds of types of loading, right. So, under these types of loading, if we manage to get the or manage to find out the strain energy, then from the strain energy we will be getting other information like deflection or the rotation, other things, right. So, let us try to determine the strain energy for an elastic system. Okay. Now, we are considering one infinitesimally small element within a linear elastic body. Okay. The previously we have considered that, okay, when we are talking about the stress, okay, distribution of stress and all. So, we are considering one infinitesimally small element, okay, inside an elastic body, okay, and that is nothing but like this. So, this is your elastic body under the action of say sigma x. So, this is your x, y and z. So, under the action of only sigma x. So, the original dimension was dx, dz, dy, okay. And due to this application of sigma x, that means we are applying one tensile stress. Due to this application of sigma x, you will be getting the elongation of the so this is the elongated body, right. So, you will be getting some elongation, unidirectional elongation, okay. Of course, the Poisson's effect will be there, but you will be getting some elongation in the x direction, okay. So, that elongation is nothing but your epsilon. If I say the strain in x direction, say epsilon x, then what I can write for this infinitesimally small element, the strain energy can be written as half F delta. Now, what is the force? Half force is, what is the force? Sigma x into dy dz, sigma x into dy dz, that is the force in the x direction, okay. And what is the elongation delta or the deformation? The delta is nothing but epsilon x dx, agreed. Epsilon x is your strain and dx is the original length before deformation, before application of sigma x. So, from this I can write down, so du is basically is equal to half sigma x epsilon x dv, where dv is nothing but the volume, dv is equal to dx dy dz, that is the volume of the element, okay, small element. So, this is the strain energy due to the application of only sigma x on the element, and that you have got sigma x half into sigma x epsilon x dv, okay. Similarly, therefore, this if you consider the whole elastic body, I mean if you consider the whole elastic body is made of this small elements, several small elements, then the total strain energy of the whole body, whole elastic body will be the integration of du, right. So, that will be okay, that is the total strain energy of the whole elastic body. So, we considered one small element in that elastic body and then we have found out the strain energy for that small element, and then if we consider the whole elastic body, then this is the strain energy for the whole elastic body, just we are taking the integration over the whole volume, okay. Now, if you consider shear stress is also acting, okay. Now, if you consider shear stress is also acting, suppose again we are considering the small element, so this is the small element, okay, and you are applying shear. You are applying shear, that is a tau xy, only you are applying the shear in xy planes, okay. So, tau xy. So, due to that you will be getting the deformed shape like that. something like that. So, the shearing, okay. So, angular distortion. So, if you look at only that in that plane, so this is your shear deformation. So, this was dy say, okay, and this is of course, this deformation will be gamma xy dy, agreed, gamma xy dy, where gamma xy is your shear strain. Okay. Now, in that situation, what will be your strain energy for that particular element du? If I write down that, okay. So, your du for that small element will be equal to half F delta. What is the force? Force is tau xy dx dz. This is the force, shear force, okay, acting on the element, multiplied by the deformation delta. What is deformation? That is gamma xy dy. So, from this I can write down half tau xy gamma xy dv. So, that is the strain energy, okay, for this small element under the action of tau xy. Now, if I consider the general state of stress, that means all the say stress components are acting. Now, 3 normal stress, 3 shear stresses. So, all stress 6 stress components are acting on this particular element. Then your du, now if we consider all 6 components, all 6 components of stress are acting, okay. So, if under that situation your du, that is the strain energy for that particular small element, okay, will be simply half sigma x epsilon x plus sigma y epsilon y plus sigma z epsilon z plus tau xy gamma xy plus tau yz gamma yz plus tau zx gamma zx into dv, okay. And the total strain energy of this whole body, this is the strain energy for that particular element. Now, when the body is consisting of several elements, then the total strain energy will be simply half integration over the whole volume sigma x epsilon x plus sigma y epsilon y and all those things plus tau zx gamma zx into dv. That is the total strain energy of the whole body, okay. Now, if you consider the plane strain condition, okay, if you consider the plane strain or plane stress condition, generally whatever we are dealing with in this particular course, if you consider plane strain or plane stress condition, if you consider, okay, in xy plane, okay, then this other stress components and strain components will not be there. So, we can simply write the strain energy is equal to half integration over the whole volume sigma x epsilon x plus sigma y epsilon y plus tau xy gamma xy dv. So, this is the strain energy in plane stress or plane strain condition. Clear? So, this is the expression of your strain energy. So, if you manage to get all the stress strain components, then basically you can find out the strain energy for a particular system, okay, particular elastic body. So, I will stop here today. So, in the next lecture we will be continuing this discussion and we will see few problems. Thank you very much.